All right, finally into the examples. So I'm going to start off with a lot of the 0 over 0 and infinity over infinity, and then I'll start introducing in some of those other types. So I would say if you watch this first video, ABC, you should be able to get started and tackle the first chunk from your homework. And as you run into something that's not a 0 over 0, infinity over infinity, come check back and watch a little bit more. So this is the one that we worked on using the tangent lines to find the value. So we already have this idea that the value is 1/5, but I just want to show you how L'Hopital's rule will work for this. So L'Hopital's rule says, well, we better check, even though we did before. Make sure you have the right form. Do not apply L'Hopital's rule to something that's not a 0 over 0 or infinity over infinity. Okay, so if it's a 0 over 0 or infinity over infinity, L'Hopital's rule says that we can look at the top and bottom totally separately and take their derivatives. So the derivative of e to the x minus 1 is e to the x. The derivative of 5 sine x is 5 cosine x. And as you plug in 0, you no longer have that undefined. Now, we don't have 0 over 0. When we plug in 0, e to the 0 is 1. When we plug in 0 in the bottom, cosine of 0 is 1, so there's our 1/5. So this is really the same thing we did before. We've just shortened the process. Instead of going through writing it all separately, finding the tangent lines, canceling the x, we just said, okay, well, the slope comes from the derivative. We're interested in the slopes at that point, x equals 0, so let's just go for it. This is not a formal notation, but I'm just going to use it so that it's easy for you to see what I'm doing. I write a little L over the equal sign when I apply L'Hopital's rule. So if you go to someone else's class, they're probably not going to do that. I do it to communicate with you when I applied that L'Hopital's rule. You're welcome to do it to communicate with me as well. And that's it. So it's actually often a fairly simple process. You use those derivatives. It works really well as long as the derivative makes whatever you're working with a little simpler. If you have functions that don't simplify a lot as you take the derivative, that could be a little bit of a problem. But it helps with a lot of things. Okay, so for part B, as b goes to infinity, the natural log of, not the left, that's the bottom, pi times the square root of b is also going to go to infinity. It does it slowly, but it will. And the natural log of b as well goes to infinity. It does it slowly, but it is increasing forever. So this is really a question of whenever you have these infinity over infinities, who gets there faster or slower? So in this case, we're going to learn whether the square root of b grows more slowly or the natural log of b grows more slowly. Since it is infinity over infinity, we can jump right into a L'Hopital's rule. Always check that first. Okay, so the top, I have pi times b to the 1/2, which means I'm going to get 1/2 pi times b to the negative 1/2 over the derivative of natural log b is a 1 over b. Okay, so this is kind of a mess. I'm going to rewrite a little bit. Let's see, this top, I'm just going to erase and redo this top right now. So the 2 goes on the bottom, the b to the 1/2 goes on the bottom. So I have a 2 root b, and the 1 is in the top, or the pi is in the top, sorry. Forgot about that. And now if I let b go to infinity, what I'm seeing is that the top is a fraction, so the bottom gets really big. This goes to 0. And the same thing here, as b gets really big, this goes to 0. So it actually still is an indeterminate form, but this is an indeterminate form that algebra can work on. So I'm going to go ahead and do a little algebra. I'm going to say I have pi over 2 root b times b over 1. And I can cancel there. So I have a b to the 1 over a b to the 1/2, right? This is 1, this is 1/2. When I subtract, 1 minus 1/2 is 1/2. So that means I have a square root of b left on the top. Pi root b over 2. And now when I plug in infinity, I can see that the square root of b is going to slowly increase to infinity, Multiplying that by pi over 2 won't get rid of that. So this is getting infinitely large, which is a valid response for what is the value of your limit. And what it tells me is that this pi times the square root of b grows more quickly than the natural log of b. So it's kind of the reverse of an x squared versus an e to the x. E to the x grows way faster than x squared. When you flip them over y equals x to get their inverses, the natural log is going to flatten out way more quickly than the square root is going to. So it reverses that, where e to the x grows more quickly, natural log x flattens out more quickly. Okay, one more of these. Limit as x approaches 3 of x squared minus 1 over x. So if we check out what's happening, when we plug in 3, we have 3 squared minus 1, which is 8 on the top and 3 on the bottom. There is absolutely no reason to apply a L'Hopital's rule to this. This is my number one warning, and the one thing I don't like about doing this at the end is it is an easy rule to go on autopilot with. So you always have to check forms. Don't forget that using algebra on these things is fantastic. I also will point out, and I'll say this again as we're reviewing, okay, so there's kind of two things happening here. This is using derivatives to find the value of certain limits. Initially, what we did was learn how to find the derivative using limits. So we've kind of flip-flopped that. So let me just point out that if you are trying to do a limit definition of the derivative, you certainly shouldn't be applying derivative shortcuts to that. That kind of defeats the whole purpose of saying what's underlying this is this limit process. So don't use don't use L'Hopital's rules to find derivatives. Okay, I think that's it for this one. So that should get you started, and then as you hit trickier ones, I've got trickier examples in future videos. Thanks for watching.